You have
I will
to
use
change
it.
the resolution.
No, it's a remote control that I will use this. Doesn't matter.
I have another remote control.
Okay, but I will go. Okay, so again, I want to thank the organizer. I acknowledge the people. And okay, since I'm the first one, I'm already late, but I will still want to tell you what is in my opinion, why one-dimensional systems are becoming so popular in these years. Well, for one thing, in low dimension, quantum fluctuation are enhanced, so it's so to speak, it's easy to reach strongly correlated regimes. On the other hand, in one dimension, there are many body models that are exactly solvable, and for us, of course, the most important one is the Lieb-Lininger model. And last but not least, also in one dimension, there are powerful numerical techniques that are really making possible to address even time-dependent dynamics in many body systems and out of equilibrium configuration. And of course, 1D system would be just an academic toy if they didn't exist in real world, but they do exist. And some notable examples are the carbon nanotubes and the spin chain incorporates. But what matters to me are quantum gases. And in quantum gases, one-dimensional BEC or quasi-one-dimensional BEC were actually started here at MIT more than 10 years ago. And then there were experiments of a number of other groups, Hamburg, NIST, and others that I listed here. But I guess that the main breakthrough came about in 2004 when the strongly correlated regime or the Tong-Jiao gas was achieved about the same time by the Weiss group and the Immanuel Bloch group. And it was also later achieved in 2009 by the group of Hans-Christoph Nagel in Innsbruck. And so this really started the many-body physics with the one-dimensional gases. And but for my purpose today, the most relevant experiment was probably the one that was done a few years back in the group of Michael Cole in Cambridge, Cambridge, UK, where an array of one-dimensional system was created by intersecting two laser beams, so creating an optical lattice in 2 dimensions, and was filled with rubidium atoms. At some point, some of the atoms in the middle of the tubes were turned to a different spin state by a radio frequency pulse, and this created a minority component which actually formed the impurity. These impurity atoms were not trapped, so they fell under gravity, and so my pulse and collaborator studied the fall of the atoms under a constant force, which is gravity, plus a drag force, which was due to the host atoms. Our experiment is in many ways similar to this because we also create tubes by intersecting 2 laser beams, by having 2 orthogonal standing waves. But our impurities are atoms of a different species. Our impurities are potassium atoms embedded in rubidium atoms. And another notable difference is that our tubes are horizontal, so our impurities don't fall. They're actually trapped by an harmonic potential like the surrounding gas of rubidium atoms. And in addition to that, we can control the impurities, the interaction between the impurity and the host atoms because the potassium-rubidium mixture features some convenient Feshbach resonance. Okay, before I show the experiment, I want to point out that this system is actually analogous, is reminiscent of a ferromagnetic chain with a spin which is flipped. So the impurity is like the spin flipped in a ferromagnetic chain. And this is what really started our interest in this system. Because in a ferromagnetic chain, a ferromagnetic chain of spins in one dimension, you can describe it with an extension of the Lieb-Lininger model. This is the familiar Lieb-Lininger model. If you extend it to include 2 components or isospin 1/2, this becomes the Yang-Godin model, which is, however, a model that has all the mass equal and all the coupling strengths that are equal. So this Yang-Godin model was studied long ago and more recently by Fuchs and co-workers. And what is interesting about this model is that it was found out that if you start from a ferromagnetic ground state, not only you have low energy excitation, which are the phonons, which have a linear dispersion relationship, but also you have a spin excitation. This spin excitation have a dispersion relationship which is quadratic in momentum. And so you can define effective mass that you can actually, you have analytic expression for the weak coupling when the Lieb-Lininger parameter is much more than 1, and for strong coupling when the linear parameter is much larger than 1. But what is important is that because these spin excitation are quadratic, this system somehow falls out the paradigm of Luttinger liquid, which assumes that the low energy physics is described by excitation which have a linear dispersion relation. And actually some interesting result came out. Again, in this work, the effective mass was calculated in the full range of Lieb linear parameter, but also Michael Zvonarev and co-workers showed that at very low temperature, basically 0 temperature, for very large Lieb linear parameters, the size of the impurity actually subdiffuses at short time. So the size of the impurity doesn't increase as the square root of t, but as the log of t. So this basically was the main motivation. As we see, I mean, you reach this regime only at very low temperature, and our experiment is not in this regime. Okay, but this is just to motivate why we started the work to work on this. Okay, so far so good for the theory. Now I'm turning to the experiment. So we start with a mixture of rubidium and potassium. Both atoms are in their lowest hyperfine state, and we cool down by evaporation in an optical trap, and we have an external magnetic field which controls the interspecies interaction. So we can tune the interaction between the impurity and the host gas. But the interaction between the impurities themselves and the atoms in the bath themselves are fixed and given by nature. Okay, so we cannot change by at least in this magnetic field range. We evaporate to the point that we have a mixture at about 140 nanokelvin. At this point, we have roughly 200,000 rubidium atoms, the majority component, and 5,000 to 10,000 impurity atoms. Then we create the tubes. Again, we use two-dimensional optical lattice. And these tubes are really one-dimensional system. And you can tell that because, well, first of all, the gap with the first excited band is much larger than the temperature of the atoms. And second, also, the tunneling time between tubes is much longer than the typical time scale of the experiment. And the same beams that create the tubes also provide the harmonic confinement, the longitudinal harmonic confinement along the direction of the tubes, which for the impurity atoms, the potassium atoms, correspond to a frequency of about 80 Hz. Okay. Okay. So we calculate that given the initial condition, we have in the central tube where we have maximum filling factors, we have about 180 atoms of the bath, of the rubidium, and about 2 atoms of potassium, of the impurities. The rubidium, for the rubidium, we can calculate the Lieb linear parameter to be about 0.5. So the rubidium is certainly not in the strongly interacting regime. It's certainly not a toxic gas. The temperature, we measure the temperature from the expansion of the rubidium atoms from the tubes. And this is like somehow tricky because depending on which fitting function we use, we get slightly different results. So here we put quite a large error bar, but I believe that probably this is also overestimated, this temperature. But nevertheless, this temperature is below at least for the central tube, is below the degenerate temperature. And so at least in the central tube, we have weakly interacting condensate or quasi-condensate of rubidium. At this point, so we have, as I said, we have rubidium and potassium in the tube, and we want to localize the impurities in the center of the tube. To do that, we had an additional laser beam, which has a very elliptical shape. And this laser beam is such that it's species selective. What does it mean? It means that it acts only on the potassium atom, only on the impurity, and it creates nearly no potential on the bath of rubidium atoms. And with this, we localize the impurity at the center of the tube. And this is the end of the preparation of the experiment. So at this point, if we take in situ images, we see a cloud of rubidium atoms and a much narrower cloud. This is the direction of the tube. And we see a much narrower cloud of potassium atom. This is probably even narrower because this corresponds to our imaging resolution. So at this point, we start the experiment by abruptly shutting off the light blade, which confines the impurity. And so the impurity are let expand. So the impurity expand. But also, since there is the harmonic confinement, after some point they oscillate. So they they start a breathing mode. Okay, so the center of mass of the impurity is basically fixed, but their width oscillates. Okay, so and here is what we observe. So here I plot the width, the RMS width of the impurity atoms, these bigger open points, and here I plot the smaller points are the width of the surrounding rubidium atoms. So as you see, the size of the impurity atoms start to oscillate in time, and we record this oscillation. And in this case, we record the oscillation when the impurity is known as, we set the magnetic field so that the impurity is non-interacting with the surrounding atoms. Okay, we measure the interaction between the impurity and the bath by this parameter, which is simply the 1D coupling strength of potassium and rubidium in suitable units, which are, for us, the 1D coupling strength of the atoms in the bath. Okay, this is just to have a dimensional number. Okay, so at eta equals 0 means that there are no interaction, and then we start to turn on the interaction. These are positive interaction between the potassium and rubidium. We increase the interaction even further up to the point that we take it to the maximum value that we can have, which is about equal 30, eta equal 30. So it's clear that the larger the interaction, the smaller is the oscillation amplitude of the impurity, and also there's a tilt. You can see it better from here. So the center of this impurity is tilted upward, and eventually it will reach the rubidium size. Okay. Again, I want to point out that this is not the center of mass motion, but the RMS width of the impurity. So we fit the width by the simplest function that we can come up with, which is a damped cosine plus a linear slope, and these are the results of the fit versus for the four oscillation that I showed you. So the first thing, which was very surprising to see for us at least, is that the frequency, this oscillation frequency, is about constant. So when we change the interaction strength by almost 2 orders of magnitudes, and this breathing frequency is constant within 5%, so which is our error bar. The friction coefficient is also constant up to a point and then increases, while this slope increases further. So let me anticipate, this is the most surprising that we have, because in a sense we were aiming to see slowing down of the breathing frequency as we increase the interaction strength. Okay, but for sure the most remarkable thing that we see is that the amplitude of the oscillation decreases. So since the frequency is constant, we sit at this point about 3 milliseconds, and we record the size of the impurity at this point as we scan more finely the interaction strength. And when we do that, so we call sigma p the peak of the first oscillation, the width at the peak of the first oscillation, and we scan sigma p versus the 1D coupling strength. And when we do that, we see that these are the data. So at 0 interaction, this is normalized to the value at 0 interaction. The sigma p is 1, and then it goes down. At some point, it seems to saturate for eta larger than 5, and this is on the repulsive side of the Feshbach resonance, modified by the confinement. But also we explore the negative side, so where the interactions are attractive, and we see about the same behavior. It's not exactly, so we have less data. It's not exactly symmetric, but still, for sure, the size of the impurity is smaller than at no interaction. So this immediately tells us that the decrease of the size of the first oscillation of sigma p is not due to mundane Mill field pressure exerted by the bath on the impurity, which would be asymmetric on the sign of eta. Okay, then we want to check that it's not that we are not just simply that this decrease of this change of the first of the sigma p, the peak at the width at the first peak of the oscillation is not due to the preparation of the sample, because well, we have impurities. We are compressing the impurities to initially localize, so we expect to increase their mean kinetic energy, And it could be that the sigma p just reflects the initial kinetic energy, which depends on the interaction with the bus, because the thermalization time changes with the interaction of the bus. So to check that this is not just due to differential thermodulation of the bus depending on sigma, what we did a different experiment. So we prepared the impurities in the 1D tubes together in the host gas of rubidium, but we don't confine the impurity. We don't confine the impurity, and instead we eat up the impurities on purpose by modulating the axial confinement at a frequency which increases only or mainly the kinetic energy of the impurity. And so at this point we see that, like here we see the axial width of the impurity atoms, potassium, and the impurity and the width of the rubidium atoms. So as you see, the width of the impurity is larger because we have heated up the impurities, and over time it remains larger because we set here the interaction between impurities and surrounding gas equals 0. But when we turn on the interaction, we see thermalization. So the size of the impurity goes down, and well, modulus some difference that it still remains goes up in time with the same slope of the rubidium atoms. So we see that we do see a different thermalization depending on the interaction time, but even at the largest interaction time that we can reach, this thermalization is over a time scale of seconds, which is much, much longer than the time scale of our experiment, which is of tens of milliseconds. So in a sense, this was our experimental, this was our experimental evidence that the change of sigma p versus the interaction strength was not due to a different preparation of the sample. Okay, so now we want to understand that, and to do that, we pick up the, no, I'm kidding. But luckily we had a collaboration with Adrian Canty and Teresa Mark. We started this experiment. And so they set up a model. And their model is, let's say, a minimal model. And it's somehow semi-empirical. So they have a model where they describe the impurity with quantum Langevin equation. So these are the operators for the impurity. And the impurity is simply an harmonic oscillator which is damped, is subject to a fluctuating force due to the bath. And the mass and all these parameters of the harmonic oscillator, the effective mass, the damping, and the fluctuating force are actually dependent on the bath. But in this model, essentially to account for the first oscillation, what you need to do is only to calculate the effective mass. And the effective mass is calculated by following this paper of Feynman that was on polarons, so electrons in crystal actually. And so they calculated the renormalized mass according to the Feynman formalism. And but the important point here is to make is that the frequency was kept fixed. And this is, of course, this is surprising. This was kept fixed because to match the observation. And I must say that this is completely different from the observation of the effective mass of polarons in a gas of three-dimensional fermions, where the increase of the effective mass was actually measured from exactly from the slowing down of the collective oscillation in the gas. So to keep the same frequency and have an increased mass, this calls for a renormalization also of the trapping potential, and this is the work that this is the direction that actually is pursued right now by Adrian Cantian and Teresa Mark. Again, in this model there are many assumptions. One of them is that the rubidium density is assumed to be uniform. So it's completely disregarded the inhomogeneity along the tubes of the rubidium bath. But it was checked that the results are weakly dependent on the exact value of this uniform density. Okay, and this is what this model gets. So first of all, the purple curve. The purple curve roughly has the same behavior, but is not in quantitative agreement with the data. So in this model, this width is nothing else but the square root of the inverse of the square root of the effective mass. So at eta equals 0, the effective mass is 1. and then it increases, and the inverse square root decreases. So this is roughly the same behavior, but it's not in quantitative agreement. And so if we, to bring it in agreement, we have to multiply the interspecies coupling trend by roughly a factor of 3. And okay, if you have a question, I'll try to tell you what I'm told, why there are good reasons, why there may be good reason to do so. But at this point, this is just a fitting parameters. Okay. Okay. Then I'm also coming almost to the conclusion. So this was let me say one more thing, that this was this model was done taking into account that the bath, the rubidium bath, is actually a thermal bath, a finite temperature bath, and it was described as a set of harmonic oscillator. Okay, in this model. Then you can go to the other limit and try to calculate the dynamics at 0 temperature, and this is what was done in the group of Rosario Fassi Square Normale Superiore Pisa. So these are the results of a similar, not exactly the same experiment, but a very similar system in which time-dependent DMRG calculation are used. Okay, and again, there are some simplifying assumptions which makes the calculation different from the real experiment. So again, the bath is homogeneous. The most important, the impurity and the bath are both in the ground state before the quench, so before the impurities are released. And the quench, so the quench meaning the sudden release of the impurity, is done at harmonic frequency, which are considerably larger than the one we had in the experiment. Okay, so these are some of the curves that are very. So I must say also that these are preliminary results that are not published yet. So okay, so these are curves that are calculated with a Liebling parameter of the bath about 10. So in the larger than what we have in the experiment. I will show later result. They also have a result with smaller Liebling parameters. And you immediately see that if the interaction strength between the impurity and the bath is small, if you change the sign, basically the oscillation looks much the same. But if you increase this interaction strength, there's a huge difference between the oscillation for attractive interaction and for repulsive interaction. And so not the frequency changes, but also the damping change. And so this is a more systematic scan. So here, the black points are probably the ones that are closer to our experiment, because the Liebling parameter of the bath is 1, and then 3, 5, 10, and infinite. And here, for each value of the Liebling parameter of the bath, is scanned the interaction strength between the impurity and the bath. And as you see, so this is the frequency of the oscillation. It has, at least for gamma equal 1, there's a considerable shift of the frequency, which is asymmetric with respect to the interaction strength between the impurity and the bath. And don't ask me what is this peak, because I'm telling you. But also this peak comes about also in the damping coefficient. So this is the damping coefficient of the impurities, and even here you can see that at least on this side the damping coefficient increases rapidly by increasing the interaction strength with the bath. Okay, for example, in our experiment, this gamma equal 1 here we have eta. This would be eta equals 6, corresponding to our experiment equals 6, which is much larger than what we observe experimentally, that are gamma of the order of 0.1 in these units, 0.1 or 0.05. So both these results are very different from what we observe in the experiment. Probably it's not surprising because, well, let me say, there are things that need to be understood in this calculation, but as I said, this is zero temperature calculation, and we are surely not at zero temperature. Unfortunately, we are somehow, unfortunately or luckily, depending on how you see it, we are in a regime which neither the an analysis at 0 temperature, no analysis at high temperature really fits the experimental data. Okay, so this is the conclusion, the summary. So I show you that we measured the diffusion, the oscillation of impurities, of the RMS size of the impurities in a one-dimensional Bose gas, as we scan the interaction strength between the impurity and the gas. Surprisingly, we found that the frequency of this oscillation are independent on the interaction strength, and we didn't expect that. And while the amplitude of the impurity is very sensitive, it decreases rapidly with the interaction strength. We set up, well, actually, Adrian and Kantia set up a model to interpret the data, which roughly capture the main, let's say, the main feature of this decrease of the amplitude, but with many assumptions and approximation. So this is certainly not the last word on the issue. And in this model, what was calculated is a mass shift of the impurity due to the interaction with the bath. And also some unpublished results are these time-dependent DMRG simulation, which are done at 0 temperature, but for this, again, we need more understanding. And with this, I really end, and thank you for your attention.
You had a plot of the friction as function of interaction. So I wonder how did you measure that? And a related question, if you could measure it directly by applying some force like gravity.
So to get the friction coefficient.
Yeah, okay. So this plot where we plot the friction coefficient is, so we have this oscillation, and the solid lines are the fit with this function. So in this function, we have several parameters. One of them is this friction coefficient. So what I'm plotting here is this parameter of the friction coefficient. Coming to the second question, could we apply a force? Yeah, yes. I mean, this is probably next on the list. So to maybe not gravity, but with the same with the same beam that we use to confine impurity, we can actually move this beam and drag the impurity and oscillate the impurity with this beam. And we want to study the amplitude of the oscillation versus frequency. So this is what we plan to do.
Sorry,
Yes.
one question. You consider the potassium as being one impurity, actually.
One atom,
And
yeah.
anyway, you have obviously a finite density of these impurities, and these impurities are bosons. So therefore, what would be the strength of the interaction between the impurities?
Between the impurities themselves.
Compared to G1D
Right.
rubidium?
Okay, G1D is just the coupling strength of like the two-body coupling strength. Okay, so for potassium is slightly smaller than rubidium. So the interaction the effect due to the confinement is very small here. So the coupling strength for potassium but it's of the same order of that of rubidium. So the three-dimensional scattering length is slightly smaller. The transverse frequency. So this is away from confinement-induced resonance. This is 2 times the transverse frequency times the three-dimensional scattering length. The three-dimensional scattering length is slightly smaller. The confinement, the transverse confinement frequency is increased by a factor 1.4 by the square root of the mass. So it's roughly the same. In this unit, it will be just 1.
And concerning the Lieb-Lininger
parameter.
Yeah.
Okay, this is a good question. Okay, this should be very small. So the 1D density is very small, but the impurity, to us, to be honest, we completely disregard the many body effects on the impurity. We have 2 impurities we considered like that are like 1 atom, so that are single atoms. Yeah. Yes.
So you said that if you increase this interaction between impurity and the bus, then you see some oscillation amplitude will saturate at some point.
Yeah.
So is that related to something like a phase separation? I mean, if you increase, well, if you consider the limit in which interaction is so strong, then I think this impurity is completely detached from this thermal bus. So in that case, I think this thermal bus works something like a potential, external potential for this impurity, and then the oscillation becomes, well, this is a tight potential, so then you cannot see much oscillation.
Okay. I must say that we have many tubes. We have a collection of many tubes. And when we took images, like the image that I showed earlier, we are seeing all the tubes together. Okay, so we took an image from above, the tubes are horizontally, and we are seeing all the tubes together. So we do not have a resolution of individual tubes. But what we do see is that when we take the images, we took images in situ. We don't. So this means that we integrate over many tubes. So we sum over many tubes, but we don't see. For sure, we don't see that. It will be hard to tell because there are many tubes where we expect that there are only rubidium atoms and no potassium atoms. So if in this tube rubidium atoms are displaced from the potassium atoms, it will be hard to tell from our images. Okay, we certainly don't see like. Sorry?
I mean, of course, from the experiment is different, but you have...
from the images. Okay, sorry. Okay, I thought you were asking about...
Of course, it's better to see.
Okay, I should ask, but I don't think that they've seen a phase separation from in the image. Yeah.
Could we have one more question?
Yeah. Can I say something more about that? Just one thing. At this, I must say that at this value, eta equal 5, if we calculate simply the mean, so actually at equal 15. If we calculate the mean field energy of an impurity with the surrounding bath, this is of the order of the separation with respect to the first excited band in the lattice. So it might be that this point out the fact that our tight binding approximation that we use, that we consider only one band, breaks down when we increase the impurity. It might be, but again, experimentally, we don't have a way to tell.
Super quick question.
Yeah, very quick. Could you put that back, your fitting curve and so on?
Filling.
No, it's very quick. No, you passed
This?
it. No. The fitting curve, the decay and exponential piece.
Oh,
so oscillation, cosine.
This.
The fitting curve, the expression.
Oh, okay, sorry. This. Oh, the fit. Okay, sorry.
Yeah, you have several parameters there to play. One thing that caught my attention a little bit, I mean, when I look at the exponential and the frequency dependence there, I mean, you have this parameter gamma that appears both on the oscillation and on the decay. I don't understand that. Can you elaborate a little bit on this?
So we have the parameter gamma that appears both. So if you have like an harmonic oscillation which is damped, the frequency is slightly changed by the damping, right? And this is let's say the free harmonic oscillator frequency, and this is the frequency in presence of damping. So the gamma is both in the frequency and in the so.
I think we just...
In this decay.
Can we maybe move on to the next?
Maybe, okay.
I think Francesco
Okay.
wants more.